Welcome to DAR Tutors for online and home tuition. Today, we're going to explore the critical topic of renewable energy sources, a key component of the IB Chemistry higher level curriculum. We will be specifically focusing on biofuels, including ethanol and biodiesel, and then delve into fuel cells, which convert chemical energy directly into electricity. By the end of this session, you will be able to distinguish between renewable and non-renewable energy, describe the production and properties of biofuels, and understand the electrochemistry of hydrogen and methanol fuel cells. First, let's establish the fundamental difference between renewable and non-renewable energy sources. Non-renewable sources, like coal, oil, and natural gas, are finite. This means they exist in limited quantities and, once used, are not replenished on a timescale useful to humans. Reserves are concentrated in specific regions, which has significant geopolitical and economic consequences. Renewable sources, on the other hand, are either inexhaustible or are replenished at the rate we consume them. Think of solar power, wind, or biofuels. They offer a sustainable alternative, being less concentrated and more widely available globally, but their disadvantage is often their intermittency, depending on factors like weather or sunlight. It's important to correct a common misconception. Nuclear power is not renewable. While it doesn't emit greenhouse gases, it relies on the fission of uranium-235, which is a finite resource. Therefore, nuclear power is classified as non-renewable due to the finite nature of its fuel source. Now let's focus on biofuels. Biofuels are fuels derived from living matter or its metabolic byproducts, collectively called biomass. The foundation for all biofuels is photosynthesis, the process by which plants convert solar energy into chemical energy. Plants take in carbon dioxide from the atmosphere and water from the soil. Using the energy from sunlight trapped by chlorophyll, they convert these into glucose, a sugar, and release oxygen. This conversion of inorganic atmospheric carbon into organic carbon is called biological carbon fixation. This glucose is then used by the plant for energy, stored as starch, or converted into other organic materials like oils. These organic materials are the biomass from which biofuels are produced. This makes biofuels theoretically carbon neutral. When they are burned as fuel, they release carbon dioxide, but this is the same carbon dioxide that was recently absorbed from the atmosphere by the plants during photosynthesis. This creates a closed loop, in theory causing no net increase in atmospheric CO2. However, this is a simplified view. The energy used for growing crops, transporting them, and processing them into fuel means that biofuels are not perfectly carbon neutral in practice. Our first specific biofuel is bioethanol, which is produced by the fermentation of crops rich in starch or sugar, such as sugarcane or corn. The production is a multi-step process. First, the plant material is ground to increase surface area. Second, an enzyme, amylase, is added to hydrolyze the starch into glucose. Hydrolysis is a chemical reaction in which water is used to break down a compound. For example, if we consider starch, which is a polysaccharide made of many glucose units, amylase breaks these glycosidic bonds. Finally, yeast, a type of fungus, is introduced. Under anaerobic conditions, meaning without oxygen, yeast uses the enzyme zymase to ferment the glucose. This process yields ethanol and carbon dioxide gas. It's important to note the balanced chemical equation for the fermentation of glucose. One molecule of glucose, CCH12O6, breaks down into 2 molecules of ethanol, C2H5OH, and 2 molecules of carbon dioxide. This fermentation process has a limit. The ethanol concentration cannot exceed about 12% by mass because higher concentrations poison the yeast. To obtain pure ethanol, the mixture must be distilled. This distillation process is energy intensive, and much of the plant material, like cellulose, cannot be fermented, which makes the overall production relatively inefficient. Bioethanol offers several advantages and disadvantages as a fuel. On the advantage side, it theoretically leads to lower greenhouse gas emissions because it's derived from plants that absorb CO2. This reduces the carbon footprint compared to gasoline. It also reduces our reliance on crude oil, with countries like Brazil and the USA extensively blending ethanol into gasoline. However, there are significant drawbacks. Firstly, ethanol has a lower specific energy than gasoline, meaning you need a larger volume of ethanol to get the same amount of energy. It also absorbs moisture, which can cause engine corrosion. Secondly, the distillation required to purify ethanol is energy-intensive. When you account for the energy used in growing the crops, transporting them, and processing them, the use of ethanol may not actually reduce greenhouse gas emissions relative to traditional gasoline. Thirdly, and perhaps most critically, is the food versus fuel debate. In countries like the USA, corn is used for ethanol production. This diverts a major food crop, driving up its price on world markets and potentially leading to hunger in poorer countries that depend on it as a staple food. Ethanol is not suitable for diesel engines, so we turn to biodiesel. Biodiesel is a fuel derived from vegetable oils, which are chemically very similar to the diesel fuel from crude oil. The general structure of an oil, which is a triglyceride, is a glycerol backbone with 3 fatty acid chains represented as R1, R2, and R3. These fatty acid chains can be saturated or unsaturated. Oils are too viscous and not volatile enough to be used directly as fuel in diesel engines. Therefore, they undergo a chemical modification called trans-esterification. In this process, a triglyceride reacts with methanol, CH3OH, in the presence of an acid or alkaline catalyst. The fatty acid chains from the triglyceride are transferred to the methanol molecules, forming 3 fatty acid methyl esters, which are the components of biodiesel. The other product is glycerol propane 1-3-pathiol. This reaction produces a fuel that is more volatile and less viscous, making it a suitable substitute for conventional diesel. Let's write out the full equation. The triglyceride reacts with 3 molecules of methanol to produce 3 molecules of fatty acid methyl ester, RCO2CH3, and 1 molecule of glycerol. An excess of methanol is used to drive the equilibrium to the right, favoring product formation. As with bioethanol, biodiesel has a set of advantages and disadvantages. Many advantages are common to all biofuels. These include a decrease in fossil fuel use, a potential for lower greenhouse gas emissions due to theoretical carbon neutrality, and the fact that they can perform very well as fuels. Additionally, biodiesel is more easily biodegradable in the event of a spill and is sulfur-free, meaning it doesn't contribute to acid rain. Now for the disadvantages. Similar to ethanol, biodiesel has a slightly lower specific energy than its fossil fuel equivalent. It is also more viscous and requires pre-warming in colder climates to prevent gelling. The food versus fuel debate is even more pronounced here, as crops like palm oil are grown on vast monocultures, often displacing primary rainforests and destroying biodiversity. The issue of biodiversity loss, especially from palm oil production in Southeast Asia, is a significant ethical and environmental concern. The economic benefits of palm oil production, including employment and export income, often conflict with environmental protection, highlighting the complex ethical issues in energy generation. We have now reached the 10-minute mark. If you are looking for expert tuition in IB A-level or IGCSE curricula, please contact our tutors. We offer comprehensive, concept-driven support to help you master challenging topics like these. Our website and contact information are on the screen now. Thank you. Next, let's explore fuel cells, an electrochemical device that converts the chemical energy of a fuel directly into electrical energy. This is a key distinction from internal combustion engines or power stations that burn fuels to produce heat, which is then converted into kinetic energy to move a piston or turbine. This conversion is inherently inefficient, with typical combustion engines being only 20% efficient. Fuel cells, on the other hand, can be up to 70% efficient because they bypass the heat step. They perform a chemical reaction, an oxidation reduction or redox reaction, at electrodes. In any fuel cell, 2 reactants, a fuel and an oxidizing agent, are continuously fed into the cell. At the negative electrode, called the anode, the fuel undergoes oxidation. Oxidation is the loss of electrons. These electrons are forced to travel through an external circuit, creating an electric current that can power a device. At the positive electrode, called the cathode, the oxidizing agent undergoes reduction. Reduction is the gain of these electrons. The overall process generates electricity. As long as fuel and oxidizer are supplied, the fuel cell will continue to produce electricity. Let's examine the hydrogen-oxygen fuel cell. It's a key example in the IB curriculum and will analyze 2 common conditions: Alkaline and acidic. First, let's consider the alkaline fuel cell, which uses a potassium hydroxide solution as its electrolyte. At the anode, hydrogen gas is fed in and reacts with the hydroxide ions from the electrolyte. It gets oxidized. The anode half equation is H2 gas plus 2OH. Aqueous produces 2H2O liquid plus 2 electrons. Notice the loss of electrons, which confirms this is oxidation. At the cathode, oxygen gas is fed in and reacts with water from the electrolyte and the electrons returning from the external circuit. The cathode half equation is O2 gas plus 2H2O liquid plus 4 electrons produces 4OH aqueous. The gain of electrons signifies reduction. To get the overall reaction, we must balance the electrons. The anode produces 2 electrons, while the cathode requires 4. So we multiply the anode equation by 2. This gives us 2H2 plus 4OH on the reactant side. On the cathode side, we have O2 plus 2H2O. Combining and canceling common species like the OH ions, which are regenerated, gives us the simple overall reaction. 2H2 gas plus O2 gas produces 2H2O liquid. Now let's look at the hydrogen-oxygen fuel cell under acidic conditions, which use a phosphoric acid solution as the electrolyte. The overall reaction remains the same. Hydrogen plus oxygen yields water. However, because the electrolyte contains H plus ions instead of OH minus ions, the half equations are different. At the anode, hydrogen gas is oxidized directly to hydrogen ions and electrons. The half equation is H2 gas produces 2H plus aqueous plus 2 electrons. This is still an oxidation because electrons are lost. At the cathode, oxygen gas reacts with the hydrogen ions from the electrolyte and the electrons from the circuit. The cathode half equation is O2 gas plus 4H plus aqueous plus 4 electrons produces 2H2O liquid. This is reduction because electrons are gained. To get the overall equation, we again balance the electrons. The anode produces 2 electrons, but the cathode consumes 4. So we multiply the anode equation by 2. This gives us 2H2 plus 4, H plus plus O2. Combining and canceling the H plus ions, which are regenerated by the overall reaction, leads to the same simple overall reaction. 2H2 gas plus O2 gas produces 2H2O liquid. While hydrogen is an excellent fuel, it has some significant drawbacks. It has a very low energy density, meaning large volumes are needed to provide a continuous supply. This requires storage under pressure in large, heavy tanks. Hydrogen is also highly flammable, posing explosion risks. To overcome these, methanol fuel cells are being developed. Methanol has a far higher energy density than hydrogen and is a liquid at room temperature and pressure, making it much easier to store and transport. This makes it an attractive alternative. The design is similar to an acidic hydrogen-oxygen fuel cell. Methanol and water are fed into the anode, and air, containing oxygen, is fed into the cathode. The overall redox reaction is the catalytic oxidation of methanol to form carbon dioxide and water. At the anode, methanol is oxidized. The half equation is CH3OH plus H2O produces 6H plus 6 electrons plus CO2. This is oxidation as it involves the loss of electrons. At the cathode, oxygen is reduced. This is the same reaction we saw in the acidic hydrogen fuel cell. O2 plus 4H plus 4 electrons produces 2H2O. To find the overall equation, we need to balance the electrons. We have 6 electrons produced at the anode and 4 consumed at the cathode. The least common multiple is 12. So we multiply the anode equation by 2 and the cathode equation by 3. This gives us the overall balanced equation. 2CH3OH plus 3O2 produces 2CO2 plus 4H2. The fact that methanol fuel cells produce CO2 is a disadvantage, but the emissions are small. Now let's work through some IB-style practice questions to consolidate our understanding. Question 1 asks us to identify a renewable energy source. The question presents 4 options. Uranium. The fuel for nuclear fission is finite, so it's non-renewable. Natural gas is a fossil fuel, also non-renewable. Biodiesel, derived from plants, is renewable. Coal is another fossil fuel, non-renewable. Therefore, the correct answer is C, biodiesel, because it is derived from biomass which can be replenished naturally through plant growth. Question 2 asks for the anode half reaction in a hydrogen-oxygen fuel cell with a potassium hydroxide electrolyte. We need to remember this means alkaline conditions. At the anode, oxidation occurs. In an alkaline environment, hydrogen gas reacts with hydroxide ions. The half equation we learned was H2G plus 2OH, AQ, 2H2OL plus 2E. So the correct half reaction is H2 gas plus 2OH. Aqueous produces 2H2O liquid plus 2 electrons. This shows hydrogen being oxidized to water with the loss of electrons. Question 3 asks us to list 2 advantages and 2 disadvantages of bioethanol as a fuel. We discussed this in detail. For advantages, you could list lower greenhouse gas emissions in theory, or reduced reliance on crude oil. Let's pick lower greenhouse gas emissions. And for a second advantage, let's say reduces reliance on non-renewable fossil fuels. For disadvantages, the 2 most prominent were its lower specific energy and the food versus fuel debate. Let's write those down. So, the disadvantages are lower specific energy than gasoline and diverts crops from human consumption, raising food prices. Moving to question 4. This is a calculation-based problem. We need to determine the volume of ethanol required to produce 100 kilos of carbon dioxide. First, we need the balanced chemical equation for ethanol fermentation. 1 mole of glucose produces 2 moles of ethanol and 2 moles of carbon dioxide. Next, convert the mass of CO2 to moles using its molar mass. Now we use the stoichiometry of the reaction. From the equation, 2 moles of ethanol produce 2 moles of CO2. So 2272.2 moles of CO2 must have been produced from the same number of moles of ethanol. Now we convert the moles of ethanol to mass. Finally, we convert the mass of ethanol to its volume using its density. The volume of ethanol required is approximately 132,700 cm3 or 132.7 liters. Our final question, question 5, asks us to compare fuel cells and primary or voltaic cells. Both are electrochemical cells that convert chemical energy into electrical energy through redox reactions. However, they have a key difference related to their operation. In a primary voltaic cell, such as a disposable battery, the reactants are contained within the cell. The chemical reactions stop when one of the reactants is completely consumed and the battery dies. It is not designed to be recharged, though some might offer limited reusability. A fuel cell, on the other hand, operates by continuously supplying fuel and an oxidizing agent from external sources. The reactions continue as long as these reactants are provided. This allows for a continuous supply of electricity. A fuel cell can be thought of as a continuously running battery. We have now reached the end of our session. We've covered renewable and non-renewable energy, delved into the chemistry of bioethanol and biodiesel, and explored the electrochemistry of fuel cells. Thank you for watching this DAR Tutors video. Just a reminder, for detailed personalized tuition in IB, A-Level, and IGCSE chemistry, contact DAR Tutors. We provide expert guidance to help you master complex topics and excel in your studies.